Hey, okay, welcome here for another online lab. This is Faraday's Law. I guess it would be chapter 31 in the Survey book. And we've been doing a lot of problems really in Survey, or in Faraday's Law. Because the fundamental physics said that there is an EMF that's produced if there's any change in flux. All right, and we then really did 3 chapters on this because we did the fundamental physics in 31, then we applied it to DC circuits in 32, and then AC circuits in 33. And that's what this one is kind of about. Well, we are going to have an AC circuit, so there's a little bit of the circuitry in there, but it's not quite like the LRC circuit that we'll do later. This is really just the fundamentals of Faraday's law. So I got the equipment set up here, and I want to explain all that, but let's talk about the theory first, because here's what we're going to do. Turn to page, I guess it's 44 in the lab manual, and you can follow along here. I'll jump over here to this side of the board, but here's what I'm going to start with. I'm going to hook up a AC power supply. Right, and for better or worse, it has an internal resistor, so I'll kind of put that there. Its exact value really isn't that important, so I won't even deal with that. But we're going to then feed this into, and this is the main part of the lab, is we're going to feed it into a coil that sort of looks like a circle. And in fact, there are 500, maybe I should just put capital N, 500 turns in it. And this is going to make our magnetic field. So I'm going to put a sub P for primary. And I'm going to pick it up here. I put it out in front so I can show you. But this is it, 500 turn filled coil. And you can't really kind of see the wires, although on the side here, maybe you can. And this is our field coil. And so I'm going to feed it through there. Then I will feed it through an external resistor that I'm going to set at 50 ohms. We'll need to know that number, so I'll kind of explain that in more detail here. But that's essentially the circuit. Now, if you let me grab my green marker, as we've done many times, is I would then get some currents coming out of here. And so I will call this currents in the primary. And since it is an alternating current, mathematically, I'll write it this way, as the maximum amount of current times sine omega t, and maybe I'll do one more step, so maximum current sine, and the omega will be 2 pi times the frequency. And that's what we'll be able to measure, and one of the 3 things we want to measure is what is the frequency. Now I grabbed the green one because I wanted you to see, and I'll just kind of put some X's in here, although that can be a little misleading, because there would be a magnetic field, and this will take us back to chapter 30, the magnetic field from a circular wire. Of course, which way is the magnetic field? And that's why I said my picture might be misleading, because at one moment in time, if I do my second right-hand rule, and I have the current going in a clockwise direction, so current in a clockwise direction, then I would get the field going in. But since this is an alternating current, there would be a moment later where the current is going counterclockwise and the field would be coming out. So I'm going to draw it as going in, but I just want to keep saying, note that it could be either way. The real key here, though, is this will create a changing magnetic field inside of this loop, which I'm going to call the primary. Because, maybe I'll grab a different color here. Faraday's law says that there is an induced voltage, an induced EMF, and in this case I'm going to make a secondary, in the secondary when there is a changing magnetic flux. And so I'm going to draw in blue here another coil. It will have a number of turns, let me say n sub s for the number of turns in the secondary. And I need to confirm this one. I threw it out here so I can grab it and show you guys. Let's see, I believe it's 400, was it? Yeah, 400 on this one. Because we have another one we'll do in part 2 that's got 2,000. But for this one, it's got 400. So let me put over here 400 turns. And of course, that's going to produce a voltage. And so here's where the math begins. What is the voltage in the secondary based upon Faraday's law? And so we're hopefully going to see a couple of interesting things, but the primary thing here today is that we will see that there is an EMF created in the secondary because of the changing flux, which of course is coming from the primary. The primary is making the field because we have a current in a circular loop, and it's changing because the current is changing, and the current of course is changing because we're using an AC power supply. And so that's how we know we will have a secondary voltage anytime there is a changing magnetic flux. So in this case, the changing magnetic flux, if you carry it back, comes all the way from the fact that the current is changing in the power supply, or the voltage is changing in the power supply, which makes the current change in the primary circuit. All right, so let me just put here Faraday's law. This would be the number of turns in the secondary times the derivative of the change in magnetic flux. And this would be the flux in the secondary. So continuing with a couple of steps of mathematics, I'll leave the negative and the number of turns and the derivative alone here. But let's write off then, or write out the flux calculation. And I'm leaving it in blue because the blue then is the flux going through this smaller secondary. Of course, it is generated by the primary, so I want to make sure that that's clear. And so let me put a derivative here. And now this integral would be the b, the dA, and cosine of 0 degrees, which of course cosine of 0 degrees is just 1. And now you can see why we are going to set this up the way we are. That is, the secondary loop and the primary will be right on top of each other, so that the flux, which goes in and out, which is the field, and the normal vector, which is also pointing out, will be in the same direction. And so we won't have to worry about this part of the calculation. Let me continue. Here's my integral. And let me go back to the green, because the field that's in the secondary is coming from the current that's in the primary, and the primary is this circle. And I'm going to trust you still remember from chapter 30, what is the equation for the magnetic field from a circle? And it looks like this. It's got the mu naught, it's got the current in it, and let me then just put current sub P, or current in the primary, that's where the current is coming from. Then it is the radius, which, if you remember from class, we use the symbol A for the radius of the circle, so maybe I'll put here A. We might change that because the author of the lab manual uses a little different symbol. I'll talk about that. But then it's a 2, then it's an a squared plus an x squared to the 3/2 power. So that's the magnetic field. Then I have the dA. Okay. Now I can simplify this a little bit, and the number of turns in the secondary go here. Oh, my bad. I almost skipped over something very important. This is the magnetic field from one loop. And so I would multiply this by the number of turns in the primary. Okay, so there's the strength of the magnetic field in the primary. Now, I said I could simplify this because number one, things like the number of turns in the primary and mu naught are constants, and as you've heard me say a number of times, they're a constant not only in space but also in time. So I can pull forward n sub p and the mu naughts. Now, this right here, the currents in the primary here's where we want to be careful. In space, it's a constant. What I mean by that is if you look at the current in the primary, everywhere along in this coil, the field coil, it's the same. And I should say it's the same at that moment in time. And so that's the one that I got to be careful here. I can pull it in front of the integral, but not in front of the time derivative. So this would be the derivative of the currents in the primary, okay, in front of the integral. Going downstairs, the 2 is a constant not only in space but also in time. So I can pull that all the way in front of not only the integral but also the derivative. And this is a fun one. I don't know if you caught this while we were doing chapter 30, but at the center of the circle, this simplifies, and that's what we're going to do. I am going to put this secondary right in the center, so everything's in a plane, at least for part 1. Now in part 2, that'll change, and we'll start lifting the secondary up, and so x will be that distance from the center. But for part 1, this then, x, is going to be equal to 0. And so when that one goes away, then this down here just becomes x cubed, and together with this a cubed, and together with this a squared becomes just 1 over a. And that's the radius. And I should say that's the radius of the primary. So it doesn't change, so I can pull it out in front of the integral and pull it out in front of the time derivative. And of course, the other thing that I need to mess with is this factor. Oh, I already did the factor of 2. So there's the 2 and there's the a. All right, so I think I got everything. Of course, I still have then the integral of a is the only thing that's left, which would be the area. So I will just put the area. And of course, now I need to be careful because area of what? And so following this back, this is the integral of the flux through the secondary. So this is the area of the secondary. So I want to put a little S right here.
Make it blue.
And I should make that one blue. Ron points out, yeah, to keep my color code. All right. Well, now that I've kind of merged them all together, I'm going to blow off my color code. So I'll just go back to black here and start saying, okay, so what do I have? So I've got this negative. I got the number of turns in the secondary, the number of turns in the primary, the mu naught, that's the permittivity of free space, so that's that 4 pi times 10 to the minus 7. And then I will go ahead and I will move the area of the secondary forward. I will go here with a 2, and let me just double check, but I am pretty sure, yeah, that your author changes the symbol from your textbook. So in your textbook, we had A for the radius of this primary. Your author here in the lab manual calls this the radius of the primary. So I'll give it a capital R with a sub P, so the radius of the primary. And I'll just even double check, yeah, that's it. Okay, now I've got this derivative, and that's why I wanted to write this out. So if I take the derivative of this, I get the currents maximum. When I take the derivative of a sine function, I get a cosine function. Okay, so cosine 2 pi ft. And then I get the chain rule, which pulls out a 2 pi.
Frequency?
And let me take, what?
Frequency come out?
2 pi f, yes, thank you. I missed that one. Yeah, chain. Good. We need that. That's one thing we've got to measure here. Okay, so with that in mind here, let me simplify this a little bit. I'll start with just canceling off a 2. I think that's about all we can do. So I have number of turns of secondary, number of turns of primary. I have mu naught. I have area of secondary. I have a pi. I have maximum current I'm going to write first, and then I have frequency. So I'm just going to change that order so we can collect our data that way. So I'll put frequency here and maximum here. Let's see, so downstairs, we'll just put the line over here. I will have radius of primary. Now I'm going to do one last thing, and I'm going to say, let's just look for the secondary maximum. Because the cosine function says that it changes, and so the actual voltage in the secondary should be following this cosine function. But if I take the maximum would be all this stuff in front, and not counting the negative sign, and not counting the trig function. Okay? And so this is our maximum. And so we're going to make a data table here in a moment. But let me do one more thing. According to this Faraday's law, the maximum voltage in the secondary divided by the maximum current would then be equal to a bunch of numbers, constants, times the frequency. Now, of course, those bunch of constants would be this: the number of turns in the secondary, the number of turns in the primary, the mu naught, the area of the secondary, times pi over the radius of the primary. Now, since there was quite a bit of math here, let me just kind of double check. He's got those 5 things in the top and 1 in the bottom. Now, so I think I've done my math right. And so here's what you are going to be asked to do, or I should say we as a partners are asked to do. We're going to hook all this up and collect data. And according to this theory that we just went through, this right here, that is the maximum in the secondary divided by the current that's in the primary, the maximum current in the primary, should be proportional to the frequency. And so we are going to try to make a graph that looks like this. On the horizontal axis, we will plot frequency. On the vertical axis, we will plot the voltage in the secondary, its maximum, and we will divide it by the current in the primary. And according to this theory we went through, and so if Faraday's law is right, that's the whole point here, not that we're really trying to question Faraday's law, but we're really just trying to emphasize empirical science, that we have a nice theory, and theory should be then tested with results, should be tested in the lab. And so we go in the lab and we try this. And so if what Faraday is saying in theory is right, then when we go to an experiment, if we measure these three things, if we measure the voltage in the secondary, the current in the primary, and the frequency, and then we plot it in this way, we should get something that looks proportional. So that's what I'm hoping we get here in part one, that we confirm Faraday's law. So I'm going to make a little table here, and the first thing I am going to measure is the frequency. And as the book says, start at 100 and then go to 300 and then continue on at a rate of about 300 hertz per step. And so 900, 1200, 1500, make sure I give myself enough room. They say go all the way to 3,000 hertz. So 1,800, 2,100, 2,400, 2,700, and finally 3,000. So there's the frequencies we will be measuring here in a moment. Okay, so that's the first column. Now, of course, the other thing we need to measure is these two. All right, so I'm going to put what is the voltage, what is the EMF in the secondary. Okay. Now, the other thing is to measure what the current is. Well, here's where I'm going to run into trouble. Because to measure the current, I am going to use an oscilloscope. Remember the last lab we did? The last lab we were introduced to the oscilloscope. So I'm going to actually take advantage of your knowledge of the oscilloscope. I'm going to actually show you a different model of an oscilloscope, one that is a little more sophisticated, one that actually does most of the measuring for us. So it's going to be really simple, but it's almost so simple that it wouldn't have been educational to show you that one. So last week we did the older models that didn't have a bunch of digital electronics. Here we can just push a button and say, could you please tell me the maximum voltage? And it will. And so it's like I said, really too easy to be educational. So, but it's nice that you see it, and that's why we like to do both. We like to show you the older models, the old analytical models, the one that really give you more freedom to do creative things with your own, and then the ones that are kind of self-programmed. Hey, who doesn't want to measure the maximum voltage? Just hit the little button that says maximum voltage. So because of that, that's what I'm going to do here today. But as I've said in class many times, the problem with oscilloscopes is they don't measure current, they measure voltage. So I'm going to take advantage of Ohm's law. I'm going to do this. I am going to measure the voltage, and here's the key. Let's come all the way back to the beginning circuit. Remember I told you I was going to set this resistor at 50 ohms, because what I'm going to actually then measure on my scope, let me call it E sub R, for the voltage on the resistor, okay? And so this right here, the voltage on the secondary, I'm going to hook to channel 2, But here, the voltage on the resistor, I'm going to hook to channel 1. One thing we didn't use in the last lab, but is worth mentioning, is that these oscilloscopes often have multiple channels. And so you can measure 2 things at once, or 4 things, or 8 things, or 16 things, depending on the kind of scope you have. Now, we don't have anything quite that sophisticated. All of our scopes have only 2 channels. So, but that's perfect for us. So we've got a 2-channel, but it's a nice digital scope. And so we're going to measure these 2 things. But here's why I say that. Because I'm going to actually measure then not the current, but the EMF on the resistor. And as you'll see, we measure in voltages. So maybe I'll just put a little 1 atop of here, because this is what I will be reading off of channel 1, and using the second channel to my oscilloscope, this is what I'll be reading on channel 2. And so those are actually the 3 things we will measure. Those are the things you need to type into graphical analysis, because then once we have those, we can then create a new calculated column, which would then give me this current. And so the current, you will then calculate by taking this column, voltage on the resistor, and divide it by the 50 ohms. And so that's the little formula you're going to put in there, okay? And so this would be in volts, and this would be in ohms, and so that means our current is going to come out in amps. And so we will have how much current in amps. So I'll say it again just to make it real clear. Our goal is to ultimately plot this ratio. So I'm still not done, but I do have then what I'm measuring on channel 2 here, and then this, which I don't measure current directly on an oscilloscope, but I can measure voltage. So I can play this little game, and I can measure the voltage on the resistor, and then from that use Ohm's law to find out how much current there is. So the 5th column is also going to be a calculated column. This is where you're going to take the voltage on the secondary, right here, so this column, and then divide it by this column, which is your maximum current, okay? And so once you make a table that has these 5 columns, you can then pick the 2 that we want and plot them. And of course the 2 that we want would be this 5th column on the vertical axis and the 1st column on the horizontal axis, and hopefully we will confirm Faraday.
Units.
Oh, and then voltage over amps would be technically volts. Okay. All right, and so there would be our units. So if that all made sense, well, let's actually collect data for part 1 and see what we've got to go here. All right, so let me circle around here to the front so I can also start my own table right here. And so here is the frequency. And so let me just kind of copy that down. 100, 300, 600, 900, 1200. I'm just going to write them like I did on the last lab. I know on the last lab I said I'd put them on the board, but after watching the video, I could see that you could see my table really well. So now that I've done everything on the board, I'm going to actually just write it here for part number 1, and then we will, you can pause the video and input them into your graphical analysis. All right, so 1800, 2100, 2400, 2700, and then finally 3000. Okay, so this is the voltage on the secondary. This is the voltage on the primary, or the resistor that's in the primary. This is going to be a formula that's going to give me the maximum, because I'm going to then take the voltage on the resistor and divide it by 50. And finally we get to the one we really want, which would be the voltage in the secondary, which is the second column divided by the fourth column. And now we can plot the fifth column versus the first column. All right, now make sure. Put some units. This is going to be measured in volts. This is going to be measured in amps, and this is going to be measured in ohms. Okay? And so let me hook it up. And I went ahead and from last week's lab left this stuff out, but here is my signal generator we talked about last time. I've got the amplitude all the way up, and if you remember, this little dial tells us the frequency. Right now we are at about 715. Which isn't one of our measurements, but I'm just going to leave it right there as I'm setting it up. So I'm going to feed this into my primary. And as I showed you earlier, here it is. And so there is the feed. Okay? Now from there, I'm going to send it to a resistor, as we said in the circuit diagram. Here's a nice little decade box. We saw this earlier, but this can dial in a lot of different resistance. I'm looking at the 10 ohms, and I just put it on the fifth setting. So this is 5 times 10, this is 50 ohms. So there should be 50 ohms here. So if I let it come out of the filled coil and go to this resistor, now at 50, and then if I complete the circuit, I now have my primary. And hopefully what you see in front here looks a lot like the drawing I did at the beginning here, where I've got the AC power supply, the filled coil, and the 50 ohm resistor. Okay. Now, as a pickup coil, here's my secondary. This is the one I was saying has the 400 turns. And so I'm going to set it so that it is reasonably close to being in the center of my primary. And so that means it right there in that little coil. In fact, I'll pick up one that looks a little bit like it. It's a little different. We're going to use this for part 2. But buried inside of here are wires wrapped around. You can kind of see that copper color under the plastic. But they actually wrap around, and on this model, it's 2,000 times. But the one we're using is the 400. So 400 times, and then the wires lead down to these connections. And so this is where the voltage is. And so, as I said on numerous occasions, I like to hook up my measuring devices last. All right. Well, this gives me a chance to turn to the fancy oscilloscope. You can kind of see the screen. Right away, you can already see it's a colored screen. But I've got the channel 1 and the channel 2 connected. This, in a lot of ways, is like the one you saw in the last lab. Here is the vertical reading, and of course, changing this dial changes how many volts per division on channel 1. This one would how many on channel 2, and this one says horizontal, and so this is the time along the horizontal axis. I've already turned it on, and both channels, and right now they just give me a 0 across the center of the screen because they're both reading no voltage. They're not hooked in. And watch what happens when I hook up channel 1. And coming back to our diagram, channel 1 is this resistor. And so I will plug in the black and then the red. And if you could see this on the screen, you can see the yellow line got kind of wavy. This one is color-coded a little bit, so you can see channel 1 is in yellow, so everything on the screen that is in yellow represents channel 1. Now channel 1 is set, and you can see down here in yellow at 5 volts per division. And so it did not go very high, so I think I would be better off to maybe increase it. So something I can see a little bit better on my screen. Although to be quite honest, I'm not even going to look at the pattern on the screen because in addition, something that the older model could not do is the computer here can actually measure it for me and then give me a display. And so with a digital display, it can actually then say what it is. And so you'll see right here, channel 1, peak-to-peak voltage, 2.48 volts. And so it actually gave me the voltage already. Okay? Now I don't want to write that down because I'm not at the right frequency that I want to write down. Well, what I'm going to be looking for, and then this is that third column, channel 1. In fact, maybe I should put in my little chart, channel 1 and channel 2, so I can keep myself straight. Channel 1, I'm just going to read right off here, yellow, peak-to-peak voltage. Okay? Now, let's look at channel 2. Channel 2, the same idea. So let me grab my 2 wires here again. And let's take a look at channel 2. Now, I hope you can see the blue horizontal line in there because the blue horizontal is the voltage I'm getting on channel 2, which of course is nothing right now because nothing's hooked up. So we can see the alternating voltage in the yellow, or maybe that's gold, and then in the blue, oh yeah, let's do gold because then it'll be blue and gold. See, and blue and gold is one of my favorite set of colors because I'm a graduate of UCLA, so that's that's UCLA football team's colors, and they actually played for the first time this year. I guess they had game 2, so they did really well Saturday. And in fact, so well they moved the game to Sunday, and so I missed it. I was all looking for it, and then the TV demands, and anyways, and they changed it because people wanted to see it, and which surprised me because they're not that great of a team really. But anyways. I digress. So I'm going to call it gold from here on out is what I'm going to. This is blue and gold, which actually happen to be my high school colors too. So there we go. So I kind of like that. All right, so that being said, let me hook channel 2 to the secondary. And the secondary, plug this in without disturbing it too much. It's right here. And that should be picking up a little bit. Now, to be quite honest, I don't see anything. But maybe that's not a surprise. I'm a little nervous. But it's set at 5 volts per division. And so this is the voltage in the secondary. And I'm not going to pick up very much. So maybe I better change it. Oh, that's really noisy. I'm picking up not just my circuits, but you can see some high frequency stuff on top. Oh, it's my microphone. Check it out.
Mm-hmm.
Oh.
Yeah. Your antenna.
Yeah. So just out of curiosity, if I get close and spread it out, I should be able to pick up the frequency and the modulation. Well, I better not get sidetracked here. But this is a new problem. And I'll tell you what I'm going to check out. Let's see if we can increase our signal to noise ratio with a little higher resistance here. So I'm going to just try something here for a second. Give me a second. Don't really like that. Okay.
When you back up, it's fine.
Yeah, when I back away, it seems to go down. And it's interesting. Now, usually we always pick up a little bit because we pick up our Wi-Fi, and so we always have a fun conversation about the Wi-Fi. But with this cordless lapel mic, it's even more interesting. Now, couple things I can do. And I'm kind of curious if I turned it off for a second. Huh. Okay, turn it back on. Hopefully you can hear me again. Okay.
Yeah, here you go.
So maybe I'll take a reading, but you know what? I'm just kind of wondering here. It's reading 240. Yeah, there is some variation. So I might just turn it off real quick to take the reading and then turn it back on and see where that gets us. Either way, I think we'll understand the physics of it, even if we realize that there's more going on here than we kind of
You can take it off here.
expected.
Come around here and take it this your way.
Huh?
If you get back here, there's no interference and you can see the reading.
Oh, yeah, I guess I could step away and let you guys read it yourself, huh? I could do something like that. But anyway, so I'm going to just continue on. But before I actually take the data, do you see the pattern? Do you see how one looks like a sine wave and one looks like a cosine? See? Maybe I'll change the horizontal positioning. But you will see, let's see, if you go back to my map, the secondary, which is channel 2, should look like a negative cosine function. And sure enough, the blue one is a negative cosine function. Now, maybe I'll swing around to this side of the board again, but it was actually in this line right here where we said the voltage in the secondary would be a negative cosine function when the current and the voltage was a positive sine function. And so it does show them out of phase. And it doesn't surprise you either for those of you who've already done a lot of work in chapter 33, because that's one of the things we were talking about. We can think of this big coil as an inductor. And so I really have an inductance circuit here. This is what I called Eli. And so we should get the voltage before we get the current. And so sure enough, if you look at the peak of the gold line, it peaks just a little bit for the blue line. The blue line is the current and the gold line is the voltage. And so we have that Eli effect. We have the voltage and then we have current. And that, of course, that is Faraday's law. Faraday's law says that, look, the voltage is the derivative of the current. So you have to change the current first before you get any current. All right. Well, finally, I think we're ready to make our measurements here. So let me kind of go, I guess, fairly quickly here. Maybe I will. This dial will not go all the way down to 100. Or will it? It probably won't do it well.
Go to 10 and come up.
So I'm going to put it here near 300. And you know what actually would be better? I should have never wrote down these numbers, because instead of trying to get them square on, let's just measure what they really are. So this says 317, and the computer here also says 317. And as I look at my monitor, it's going off the top, so maybe I'll turn channel 1 down here a little bit. And so let me just put right here, 318 is the frequency, and well, turn off my sound, okay? And so channel 2 is channel 2, 0.168, and channel 1 is 4.84. Okay. Now I'll turn the sound back on. So, hello again.
Right.
But I measured the primary one, which is right here. What is the voltage? And it was 484. And then the secondary one, which now it's around 200, but I think that's because I put my lapel mic back on, and that's 0.168 here. Okay, so with that in mind, why don't I switch over to something near 600. Okay. And I'll take a reading here. So this is 595 for the frequency. Okay. And I'll turn off the mic again. And I get 200. And 2.96. And I get a secondary of 0.192. All right, turn that back on. Okay, so there's 600. Let me go something close to 900. See where that gets me, a little more maybe. And give it a chance to reset, and let's make a near 900. Oh, 899, pretty close. So let's take an 899 reading, and turn off the microphone. And so 2.04 and 0.196. Okay, let me try another reading. Let's go to about 1200. All right, let's see what that gives us. I thought that'd be a little closer to 1200. But there we go. We'll call that. All right, so let's take 1193 for the frequency, and then we'll power down again. And we will get 0.200, 1.56. Nice. All right, I'll power back up. Hope you can hear me. And let's go to near 1500. In fact, actually, channel 1's getting so low. Let me change the settings so I can see it a little better. Okay. And we'll go to 1500. And there's kind of a fun subtlety here if we're beginning to understand the electronics of chapter 33 here. But if you'll notice, all of my voltages for my secondary seem to be, well, this one's a little lower and doesn't surprise me, but once I get to a certain level, they seem to be about the same all the way down. And that's true because remember about our inductors. Our inductors, the impedance of an inductor, maybe I should call reactance. The reactance of our inductor is a function of the frequency. So when I get to a high enough frequency, all the inductance, or excuse me, all the impedance is from the inductance or the reactance of the inductor is probably the best way to say it. So the fact that I have a 50 ohm resistor in this primary circuit doesn't really matter anymore. And so as I turn up the frequency, the corresponding impedance goes up and I get less current. And the, I didn't say that well. Now I'm drawing a blank here. The current will drop. Yeah, and then the resistance balances it, so I always get the same voltage. And so that's kind of a surprise when you first look at it. All right, so I'll keep going here. I'm still questioning, but I hope I said that right. Because, watch again. So we should be what, at 1500? So we're at 1503. And I want to go ahead and make these two measurements again. So I'll turn this off. All right, and so what do I have? Yeah, see, I still have my 0.22, and I get my 1.22. Right. Turn it back up. Yeah, so again, on that secondary, and that's what I said wrong. I apologize. I realized it when I turn off my power. The one that's staying constant is in the secondary. So let's see if I can say it better. So as you go to higher and higher frequencies, the reactance of the inductor goes up in proportion to the frequency, and therefore the current in the primary goes down. However, in the secondary, you pick up the voltage in proportional to the frequency. So you're picking up more voltage because we're at higher frequency, and at the same time the current is going down by that same factor, and so you end up having exactly the same voltage in the secondary as you change the frequency, at least once you get to a high enough frequency where the current is only affected by the inductance effect of the coil. That's not quite true when the current is affected also by the resistance, because the resistance doesn't change with frequency, but the reactance does, or not the reactance does. So I apologize, I didn't say that really well, so I'll say it one more time again here. The current in the primary goes down by a factor of F, but the secondary picks up the voltage by a factor of F because of Faraday's law. Those two factors balance each other, and so at a high enough frequency where only the inductor part in the primary matters, you keep getting the same voltage. So I'm not going to be surprised if I go all the way down here and I'm always getting 0.2. Okay. At lower ones, it should fade off. All right, so let's try this again. 1800. Bumped it out of the center. My cord got caught there. All right, and let's see if I'm still getting about the same amount now that I bumped it. That's going to be a bummer. And get it back in the same spot. It won't be a fair comparison. Okay, I just need to turn on my sound there for a second to check. I think I'm back in the same center there. All right, so let's take our measurement here. So the frequency is the 1807, and let me just turn off my mic. And I am looking at 1.02 and 0.200. Nice. Okay, and so there's my 18. And I don't know if I can quite get to 21. Oh yeah, just went over 21, so that's good. Looks like, don't have to go to the next setting quite yet. Okay, and we'll go and collect some data right about here. Looks like I'm at 2097. And I'll turn off my sound. And this is 0.880 and 0.20.
Oops, can't see.
Oh. Yeah, no, I'm blocking it here. Maybe I'll still get it there. All right, and now let's go to 2400. I will have to switch to a higher setting here for 24. And let's put it right about there. I'll even just kind of spread it out, maybe look at the gold one a little bit more. All right, and so it looks like I'm at 20. Yeah, I'll read it off of here. Let me stand away. We call it 2400. Looks like on this, well, turn off the mic so I can get a better reading. That says 2395, so now I'll just go 2400. Yeah. Okay, and then this is the 0.200 and 0.764, 0.764. All right, sound back on, Ron? Okay, good. All right, let's do two more and go back to our first one, then we can go to part 2 of the lab. So here's 2700. Whoa. And maybe I'll just take a reading there. I'm a little bit high, and it interferes a lot. So I'm going to turn this off and take all 3 measurements. So this is 2760. This is 0.200, and this is 0.664. Alrighty, and then one more on this setting at 3000. And I'll turn this off and say, alright, let's take a reading at now that says 3,100. This says 3,200. Let me stand away. I wonder which one I should trust. All right, let me try that. All right. And it says 3,050 on here and a little bit different there, but I'm going to take that one. And then 0.608 here and 0.200. All right, can you see those, Ron, on the video camera?
Yeah.
Good. So, all right, so I think you guys can see these measurements. We need to go back to one more measurement on the 100. And so let me go all the way back to about here. I'll make a couple of adjustments on the scope so I can see it. But as we have said many times before, I don't know how relevant what we see on the scope is, because we're just using the digital display to give us our numbers. All right, so let me turn off the mic and write down the last one here. So frequency of 93 at 8.32 and 0.088. All right, so that's that real low frequency where the primary circuit is more affected by the resistance than it is the inductance, and so it dramatically affected. And so like I said, once we get up to about here, it's just going to stay constant. And if this was a face-to-face setting, I always get the question as I start walking around. Students all, hey, it was changing for a while and then it just froze. I think something broke on it. So no, that's exactly it. Because again, you get less current because the reactance of the inductor is a function of the frequency, but also the voltage you pick up in the secondary is a function of the frequency. And so one gets reduced by a factor of the frequency, the other one gets increased by a factor of the frequency, and they balance each other. At least if there's only an inductor involved. And so that's why I said at high frequencies that would be true. All right, I'm going to leave this here. This is going to be part one. And so now that you have the numbers, I want you to go to graphical analysis, and I want you to put those in, and then I want you to make two new columns. And as I said, the fourth column is to calculate this current, which is then just basically taking the voltage you get here in column 3 and divide it by 50. And then I want you to make this fifth column, which is column 2 divided by column 4, and put that there, and then plot column 5 versus the frequency, and hopefully you'll get this linear relationship that we have here. Okay, so there's our first test of Faraday's law. Let's move on to our second test. And it's really kind of the same thing. A little simpler even, but it also gives us a chance to kind of review. Excuse me, before I leave part one. I almost forgot. You need a couple of other little measurements. Come to the board with me. Okay, so coming here to the board, you are asked, and let me just double check. See, what I just described to you was step 8. Step 8 says, using graphical analysis, plot, and they say plot this on the vertical axis, okay, and then plot this on the horizontal axis, and you should see a straight line. And then it says curve fit it. Okay, so do that. But then there's one last part of part 1. It says, when you curve fit it, the computer will give you a slope. Okay. All right, so curve fit it and get the slope. But then they ask you to compare it to theory. So theory would say, this right here is the slope. And so the slope is all of these things multiplied out. And for you to do that, I need to measure for you the radius of the primary, and for that matter, the radius of the secondary, so that you can actually do this calculation. I'll help you with it. But here's the number of turns in the secondary, which we already said was 400. And the other one is the 500. So this should be a 400. This should be a 500. The permittivity of free space is the 4 pi times 10 to the negative 7. This is the one that I need to work with you here. What is the area of the secondary? Since it is a coil in a shape of a circle, I'm going to say it is pi r squared. And then this is where, and these are not the one I use, but these are the same size, so I'm going to measure this one, where I have to actually then measure this. And here's where I'm going to kind of fudge it a little bit. As you will see, there are so many turns here that some of these wires have a small radius. In fact, the diameter is about 2 centimeters for the inner one. And then the outer one, by the time you wrap it around here, is 4 centimeters. So some of these are bigger than the other. So we want the average of the square. So why don't we take the inner and the outer squared, add them together, and divide by 2. So we can get kind of an average effect. Okay? And that'll save us from having to do an integration, but it's an integral according to the area. It's proportional to the area, so it would be r squared. So I'm going to write this then. Maybe I'll leave the pi alone. But let's take this as the 0.02 and square it, and the 0.04 and square it, and then divide by 2. So it should be roughly about 3 centimeters squared, but not exactly because, right, they're squared, so it's a nonlinear relationship. So we could just kind of average the r's and get a 3 and then square that. That would almost be the same as averaging the squares, but you guys are sophisticated enough that I think you see the difference between averaging the r's and averaging the square of the r's. The square function is, non-linear. So it's probably a little more accurate to average the squares of them. So I'm going to average the squares. All right, so there is the area, and that's what you needed me to measure with you. Let's not forget the pi here. So there's actually 3 pi's in this whole piece up here, because there's a pi in the permeability of free space, there's a pi in the area of the secondary, and there's a pi already, which came from the frequency. And being this close to Thanksgiving, what could be better than 3 pi's, right? So it's perfect. And then we have to divide all this by the radius of the primary. And so let me come over here and measure that one.
Got a duplicate.
That one may not be the same, because I was going to measure that one. Didn't quite want to do that. But let me come over here and kind of do the same. There is an inner radius of about 19 and a half. And let me try that. Yeah, I'll go 19 and a half. And then there is a bigger radius of about 23 point, let's call it 2. So 23.2. So what did I say, 19 and a half and 23.2. And divide that by 2. So I'm going to average the r's, right? I'm not averaging the r squared. I'm not trying to average the area. I'm trying to average the actual r here. So this is a linear function. And so, oh, sorry, excuse me. That's diameter. That would have messed you guys up. Divide that by 2. Divide that by 2. I did diameters. Oh, and I did the same thing here. Oh, wait. I did, didn't I? Glad I got that. I was doing inner diameter. Easy mistake to make. Careless mistake on my part. So let me try that again. Divide those by 2 to get radius and then average them, okay? And then over here would then be a 1 squared and a 2 squared. Okay, good. That would have really thrown them off. Ron, you looking at me like I'm crazy. Did I miss something?
Meters or centimeters?
Oh, and then this is in meters.
Good.
Yeah. So I've done all this in meters, and then this permittivity and free space is the big one, because that's in meters and amps and Teslas. Yeah. And so you've done all this and the same thing. So that's the part. I apologize. I almost forgot about part 1. That you are asked here in step 10 to do a lot of calculation here. Calculate all this together to see the slope you get in theory and the slope that you got in practice, and hopefully they agree with each other. So if I didn't make any other big mistakes, and I caught all the other mistakes, they should match here. All right, so with that in mind, let me go into part 2. And part 2, again, is a test, or a confirmation, if you will, of Faraday's law. It looks a lot like this here. So before I kind of erase anything, let's see how much I could use of this. And we are going to do a lot of the same thing, and that is we are going to use the primary circuit exactly the way it is. We're not going to change anything here, except that we're not going to worry about picking up how much current is in it. So for part 2, we will just bypass this 50 ohm resistor that I was using as a way of using Ohm's law and the oscilloscope. Remember, the oscilloscope can only measure voltage in order to get the current. And so we're not asked to do that. What we are asked to do is to see what we would pick up if we changed X. And so instead of changing the frequency, we are going to change X. So let me come back to this whole derivation, part 2 here. And let me erase everything after the step right here where I said set X equals to 0. Because I'm not going to do that anymore. That's what's going on here in step 2. And so, let me grab a dry rag here. In part 2, let me put the EMF in the secondary is, and so let me continue to do this. This would be minus the number of turns in the secondary, and like we did before, except we won't set X equal to 0, we could put the number of turns in the primary out forward, okay? We could bring the mu naughts forward, okay, good. We could then have the derivative of the current in the primary, so we'll come back to that. Then, right here, I guess I can bring the 2 out. But I don't maybe do this in 2 steps. Let me leave it as an integral here. This right here, remember, is the radius of the primary. And then I want to leave X as a variable. So let me write it this way. Radius of the primary squared over radius of the primary squared plus X squared to the 3/2 power. And then, of course, the area, and adding up that over the secondary. Okay. But for a given position of X, so in other words, in part 2, here's what we're going to do with our secondary. We're gonna hold it here, and then we're going to move it away. X, 1 centimeter, X, 2 centimeters, X, 3 centimeters, X, 4 centimeters. But for a given value of X, so in other words, X is not a variable here, this would just pull out in front. And so this would be number of turns in the primary. Secondary, then primary. Secondary, then primary. mu naught over 2. This right here would just be the radius of the primary squared over the radius of the primary squared plus X squared to the 3/2 power, and then pull that in front of the integral, and then this is just the area of the secondary. This right here is the derivative of the current in the primary. This would then be the maximum current in the primary. Then times the derivative, and if you let me take the derivative, I would put a cosine 2 pi ft over here, and the chain rule would give me a 2 pi f here. Now if you let me play the same game that I did in part 1, I could write the EMF in the secondary slash maximum. Okay, so there's going to be the maximum. To get the maximum, I just won't worry about this here or the negative side. So this would be number of turns in the secondary, number of turns in the primary, the mu naught, the I maximum, the 2 pi f, the area of the secondary, the radius of the primary squared, factor of 2 can drop off, and I get radius of the primary squared, and then the x squared. You see, here's what I want to do for part 2, is I want to collect some data at a given frequency and don't change it. So what is different here in part 2 is this frequency is not a variable. In fact, they even say, part 2, connect to 2000, what does it say, what frequency to use? Huh. Oh, they said set it to 500, there it is, so back in step 1. Okay, so let me just do this. Let me think about all of this stuff right here as some big constant number, right? Because I'm going to set my frequency near 500. I probably won't get exactly 500, so we're going to have to make sure we know what that is. We're going to need, oh, my apologies. We do need to measure this. Forgot about that step. Okay, so I'm going to leave this in. Well, I'm trying to get more current out of it. Okay, so to measure that number, we need that. So let's make sure we get all of these numbers. But if you'll let me do this, if you let me call all of this a constant, how about the symbol would make a good constant symbol? I don't want to use A, I've been using that for area. I don't want to use B, I've been doing that for magnetic field. Capital C, that'd be okay? All right, so I'm going to call this capital C. Actually, it might be good for constant. All right, so there is it all. Let's call all of this capital C. Then we have the radius of the primary squared. Downstairs, we have radius of the primary squared. Then we have the x squared to the 3/2 power. And so what this is saying is if I make a measurement of what is the voltage in the secondary for different distances away, and I will measure the distance in meters, and I will measure the voltage in the secondary as volts. And we are asked to do 0, and then 1 centimeter, 2 centimeters, 3 centimeters, and we are asked to go to 10 centimeters. Let's go a little further. How about we go to 20 centimeters? Okay? And so let's collect a bunch of data. And I won't make the whole chart here because I'll make that in front here as we collect the data together. But what this is saying then is if you plotted, then, this is what you're going to be asked to do with the data. If you plotted the voltage that you're picking up in the secondary as a function of x, and so voltage that I pick up in the secondary as a function of x, it should follow this mathematical pattern. What I like about this lab is even though it's Faraday's law, This is the pattern of the magnetic field from a circle. So we are really going to be plotting what does the magnetic field look like as you move off the center of a circle along its axis. This is that mathematical equation. We only are then changing the field so that it will induce a voltage into our probe. And so this is a way of measuring the magnetic field. You might remember the magnetic field lab we did. The magnetic field lab, if you recall, we did a solenoid first, then we did a toroid, then we did a straight wire. We never did the circle. And the reason why is this was coming. We can now plot the shape or the mathematical shape of the magnetic field as we move along. The way we are picking it up, though, is because the magnetic field we are creating changes with time. And so we're not actually measuring then the magnetic field, we're measuring the induced EMF created by that changing magnetic field. But it's of course proportional to that magnetic field. So hopefully we will see something that looks like that. Because that is what this equation down here says. You can see for small values of x, this radius of the primary dominates, and you just have a constant. And so you're going to see that at the beginning part, we have pretty much a constant magnetic field. But as x starts to get bigger, x starts to come into play, and eventually x gets bigger than RP, and eventually it dominates it, and once it really dominates it, this, if we could ignore that, you would see would be x cubed. And so this part should be tapering off and proportional to 1 over x cubed, where up here should be about proportional to a constant value. And so it's going to transition from a horizontal down to a 1 over r cubed. That's what the math says anyways. So let's see what we get. So like I said, this is a good one to in the sense that we're going to use this to confirm Faraday's law again. But it's also kind of nice because it brings us back to chapter 30 in the magnetic field one, and we're really measuring the strength of the magnetic field from a circle. All right. And then you are asked, and don't let me forget after I collect the data, that you're going to do a curve fit on this, and you're going to see what you get on your curve fit, and you're going to be able to compare it to the radius of the primary and the constant, which would be all these things multiplied together. That's why I said I need to make sure I measure not only the frequency for you, but also the maximum current, so that this works out well. Okay, so let's start collecting this data. All right, so let me come around here to the front. Excuse me. Probably a bad time to check, but I want to make sure I turn my microphone back on from the last
It's been on.
Yeah. Okay, and so let me take this data from part 1, toss that over here a little bit. Let me call this part 2. Let me make a little chart here that you guys are going to curve fit. So here is x in meters. And this will be a 0.01, oh no, sorry, 0. 0.01, 0.02, 0.03, 0.04, 0.05, 0.6, 0.7, 0.8, 0.9, 0.10, 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, 0.17, 0.18, 19, and 20. All right, so there is my x value. And so let's see what I pick up in my secondary. All right, so as we mentioned, I think it's always best to Well, I was going to disconnect it, but I guess it's really the same circuit, so I won't even bother to disconnect it. So I have the same circuit, although I do want it at a frequency of around 500. And so make a note here that I'm going to perform the experiments, and you'll need that as you check the values of your curve fit. One of the factors in there is what frequency we're at. So we are at 494 or 495 hertz. Okay, so there's our frequency, 494, 495, bouncing around in there somewhere. This one says 494, so maybe I'll go 494. Okay, so then, let's see, and I first said I was going to take this out, but then I realized I need to put it back. Okay, good. And maybe as long as I'm here, we really need that maximum current in our calculation. And so that's going to be the voltage that I get on channel 1 divided by the 50. So as I look here on channel 1, I'm at 3.52 volts. So let me come over here and point out that current maximum is 3.52 volts divided by the 50 volts. Okay? And so as I said, later on you need to compare all of these, and so you know that, you know that, you know that. Now you can figure out what that one is. You know the frequency. The area of the secondary, well, that was like we did before I erased it, but right, the inner radius was 1 and the outer radius was 2, so we squared them and averaged them. So that's that number. The one thing did I measure the primary last time? I did, good. And so you have that too. All right, so good. I don't need to go back and measure everything. So again, you know all of these, and you're going to be, these things right here are the C, and of course the radius of the primary, and I forgot what they were. Wasn't the diameter like a 19.5? Yeah. The inner one and the outer one was 23.2, cut in half because that was the diameter. Anyways, so you know those numbers. So good, you know those numbers, and you have enough information to get this number. So we'll be able to figure that out once we do the curve fit. All right, so let's get to the data collecting. And the data collecting might be a little tougher now that I realize my microphone gives me a problem. Because I'm going to switch from this detector, which only has 400 turns, which, coming away from it, we need something a little more sensitive, and this has more turns to it, 5 times more turns. So this can pick up 5 times more voltage. And so this has 2,000 turns. So I will hook that up. Now, sadly, if it's more sensitive, it's probably going to pick up more from my microphone. So maybe I might just turn it off and collect the data, just leaving the microphone off, and then I'll pop back on here. But if I were to put this right at the center here, and then you can see it picks up a lot more than it was before, 5 times more than it was before. And actually, with my microphone on, that might be a better one to do even for part 1. But we still have that same kind of effect here. So let me start to the best of my ability collecting the data, and I might need to kind of stabilize myself as I try to hold the wands here in place, and so I might give myself a chance to take advantage of this. All right, and so I'm going to start recording these, and I'll turn off my transmitter here and see what we get. All right, so my voltage is 0.920. 3.5. And so if I come up to here, .904. So that's 5.5. 856. 856. Let me just 3.5. Okay. So at 6.5, 0.816. So we get 7.5.
What's the left-hand column? Far left column?
Voltage. In the secondary?
Way over to the left.
Oh, this is the extra distance between 0 in the center and the top of this, so I can just keep track.
Okay.
I'll explain that when I turn my mic back on.
This is still recording some sound. This microphone here.
Oh, because when I turn that off, I can still hear?
Yeah, it's very poor sound compared to the other, but yes, there.
Ah. Yeah, so maybe they can hear a little bit. But I'll just try to go quick here. 16.5. All right, hey, well, I'm back. And let me explain a couple of things here. I was trying to make the measurements as I would go up higher and higher again. In case you were wondering, I made another column. You don't need to write this down, but just so that I could make my measurements a little cleaner, I noticed that the top edge of this was 3.5 centimeters above the table. So what I ended up doing is starting, so 0 for the pickup coil would have been when this top was 3.5. So it just made it real easy for me to kind of look at the top, and so that's why those numbers were there. So let me just cross them out for now, but that then is what you really want to know. The distance, the pickup cable is above the center of it. Sadly, another thing you might have seen while I was doing it is this little wire kind of got in the way. I couldn't pick it up any higher, so I had to disconnect it and reconnect it, and in the process of doing that, you got to always wonder about the next measurement if you didn't change anything. And the fact that I got the same measurement makes me go, ooh, ouch. But that's what we have, so go ahead and plot it. The other thing I noticed with this is, notice near the end, I don't think it changed as much as it should. You can see that if I just kind of hold it up in the air, I think even with my transmitter off, so besides picking up my transmitter, we're picking up all kinds of other things in this room, and it doesn't surprise me. That's been normal. The only thing new is my lapel mic, but we've always had troubles mostly with that Wi-Fi, but we've got other signals. We're not used to having the video camera in here. I'm probably far away, so I don't think I'm picking up anything from the video camera, but I bet I can pick up something from the scope or something from here. Yeah, see, you'll see it change a little bit depending on the orientation and the closeness of it, but mostly it's that Wi-Fi. So that's why I wanted to go to 20 centimeters. The book said go to 30 centimeters, but beyond 20 centimeters, we just got too much other noise in the room, what we're picking up, and we don't really see the pattern we want, and that pattern is the magnetic field from here. So I'll say it again, you plot these numbers and then do your curve fit, and hopefully you'll get something very decent. It probably won't be that accurate. Hopefully it'll just be even somewhat accurate enough that you'll see the pattern I was showing. And in fact, let me take the last minute here before we kind of wrap it up. If you want to take a good look at the numbers there, let's come back here to the board, and let me just say it again. I'm hoping that you will not only confirm Faraday's law, but that you will get this type of pattern. And of course, then, when you do your curve fitting, your computer will tell you what it is calling the value of C and what it is calling the value of R, because you are plotting this column versus that column, okay? And so you are asked in this last part here, your author says, make this plot and see how they compare. So I'll say it again. You have all the information you need to calculate this out, and so when you do your curve fit, look at the computer and see what the computer is giving you for this value of C, and then see how it compares to what you've got. And this has a lot of challenges with it. So if it is way off, so be it. Don't sweat it. But I think we'll still get a lot out of the lab. Okay. But let's see how close it gets. And the other thing the computer will give you is the value of your average square.
It's okay.
Oh, did it go off?
I was wondering whether the sound was going in and out, louder, quieter. This plug is moving.
Okay.
Move it again.
All right. Well.
That quick.
So
So it sounds like going up and down the whole time. I think, why is it going louder and then going quieter?
I know I've been talking here for a while, So let me show you one last thing. And that is, I thought I would actually start graphical analysis this time. Okay. Okay. Huh. Ah, nice. All right, and so I thought I would actually start graphical analysis. Try it one more time, don't want to give up. Don't want to look on the way. Double hitch up there. Yeah, fits you. Okay, so I'll do that, and then let me turn this on here and just let it kind of warm up, because I know the last time I did graphical analysis, quite a few of you, and I think because didn't have as much experience 21 didn't really see where the curve fit was. Although now that you've been through that one, when you define your own function, I think you could probably find it this second time. But I'm going to turn it on nonetheless to show you. So here we go. Here is my desktop. And of course, you'll have to do the virtual machine from home. And on that, you will see, and I'll use the laser pointer, this right here, graphical analysis. So I will double click on graphical analysis. Let me not put in all the data. But if I leave this as an X and I call this one here, I'll just call it E. I don't really have a script E, but that'll be the voltage of the secondary. And if I had some data like 1, 2, 3, and some other data like 4, 5, and 6, okay? When I go to do a curve fit, I would go here to Analyze. I'm going to drop down here to Curve Fit, and here's what I wanted to show you. It's that button right there, Define Your Own Function. So in this case, I can click here, Define My Own Function, and it will then give me a place to type in the function that I want, okay? And you can put in your constants. I'm going to suggest that you do the same symbols that I just did, which would be C and R for the constants. The variable X is given away because it says function. And so you got to write in terms of X. And so it knows what the X is. And the other things it will just take as a constant. So I would type it in this way. I would say it would be C times R caret 2, and maybe I just, for clarity, on my own sake, I will put the numerator in brackets. Okay, so there's the C and there's the R. And then I will divide it by, and then again I'll have to put this in brackets. This would be an R caret 2. And then R caret 2 plus, and then the X it'll recognize, caret 2, close bracket, another caret, and just to not have to worry about more parentheses, I'm going to say it's a power of 1.5. So 3 divided by 2 is 1.5. And so when I click OK, it should put it at the bottom and say, okay, is this what you want? And it will look at your data, and then it'll tell you what your C value and your R value is, and you'll see the plot to see how closely it represents your data, okay? And so that's how you're going to compare it. One last warning, though, because I deliberately used some different symbols than what your author did. Your author, for better or worse, did something like this. And I'm sure it was to keep it simple. I'll put it in red because I don't really like what he did here. He said, well, let's just call these a constant. So let's call all of this the constant B. Bad choice, because that looks like magnetic field to me. But okay. And then he said, let's call this constant A, which again I would say bad choice, because that looks like area to me. But in case you need to reference the lab manual as you're reading along, note that he is calling this A, the radius of the primary, and the B, all this stuff multiplied out. In fact, I should just kind of check that he and I have the same thing. He's got the mu naught, he's got the pi, he's got the primary, the secondary, the R, the F, and good. Yeah, and so we're in agreement with that, but not a good choice by my standards. All right, well, I talked a lot, hopefully not too much, and hopefully despite the trying to do a lab online, and we're kind of partners in this, I'm your hands as you kind of watch, and hopefully you'll get something out of that, including things like not just Faraday's law at this point, but kind of seeing these new, more sophisticated scopes, and something to work with that. All right, so I will see you next lab. Bye now.